Okay. So in last class we were, I think, in the mid process of implementing the neural networks, and uh, I think we had gone through the main function, and we were just about to run the code and see. So let me execute this and go ahead. So we start with loading all of our packages. We check our files. Okay. Since this is running in Colab, I need to upload the data again. I'll do that now. File. Let's give it a few seconds. It's taking some time. Okay, let's upload it. Let us try to run this thing. Okay, so we load our input and output data. We split it into train and test. Check the size. See the division of data for train and test. Some examples of the data. Here, no, run this. That is, check our neural network status. Talk about layers. Initialize random weights. So here the structure is we are having just 3 layers, 400 input layers from our data, 25 hidden layers, and then 10 output layers. Okay. Define our activation, sigmoid, and sigmoid gradient, and softmax. So we were here, I think. Did we discuss this function, or do you recall?
Yes, we have. I asked for what is that? It's step out and all. Yes,
yes, yes. So the key maybe items here. Let us still go through because this is the main function. Here we define one iteration of all the examples for one feed forward process and one backpropagation process. The function called as NN cost neural networks cost function takes into account the parameters. So we start with some parameters initial, and then in this step we update those parameters. No, in fact we don't update. We just evaluate the gradient, and so we know for sure that updating of the parameters has to happen outside this function. We define the input layer size, hidden layer size, number of labels, the data that we pass, features, and then the labels. And if we want to pass some regularization, we define theta 1, theta 2. That is, these parameters, NN parameters, are are unrolled parameters. That means that it's just one big uh, single dimension array of all the parameters. But since we want some structure, at least while running the program, we uh, extract these parameters into two parts, theta 1 and theta 2. Theta 1 links the input layer to the first hidden layer, and from the hidden layer to the output layer is linked by theta 2. So we have all of our parameters. We here in line 3 and 4. Then we define the gradient uh, in line 6 and 7. That is, we initialize our gradient with all zeros. We define the total number of examples. We define X, which is our input layer. So here again, we need to remember that since in this option, in this way of implementation, we have converted our bias term. Instead of doing it separately, we are adding it into the same theta. That means that we need to increase the size of our input layer by 1 by adding a fixed activation of 1. So we do that by this code. Then we start with saying let the cost be 0, and then we'll go through all of these examples, all of our data points, and then see what cost we get. So for each single example, we do feed forward, we get the cost, we do back propagation, and we get the gradient, the total gradient for all of the parameters. So how does the feed forward work? It says that A1, which is also our input, we say that X of all of nth row, all columns is just A1. A1 times theta 1, that is dot multiplication of A1 and theta 1, gives us Z2, which is just the weighted sum. To this weighted sum, we find the sigmoid, and after finding the sigmoid, we do an H stack with 1 so that we create the next layer, A2. So this A2 is of the right size because we have already added the bias, and the sigmoid of Z2 gives us all the other activations. Once we have our A2, we can go to the next layer by doing theta 2 times A2, which gives us Z3, and sigmoid or softmax of Z3 gives us A3. So why are we doing softmax? Because we want all of our output layer to be divided in percentage and not just some uh, some non-linear weighted function. The percentage is helpful because it is more meaningful to us, at least when reading what our model is trying to suggest. Okay. Once we have the output layer, we have some sense of cost. So here the cost equation given in 23 is binary cross entropy, and this is standard cost function for neural networks. So we evaluate the cost, and we in fact increase the cost for each example. So for one example, we evaluate it. For every other successive example, we are incrementing the cost again. We define back propagation, which is now we need to know what is the error, and based on the error, we need to say find the gradient of all of these weights so that we can correct them in the next step. Okay. So for that, we are doing back propagation. We say the output layer is wrong by A3 minus yn. That is the error of just the output layer. which has to guide us in our journey backwards in backpropagation. So with theta 2 or the transpose of theta 2 with multiplied by T3 and with sigmoid of gradient Z2, it gives us the error for all of the terms at layer 2, and then that's it. So it gives us all of the errors at layer 2. So this is the error between the hidden layer and the input layer. And once we have this D3 and D2, we can uh, multiply them or with our A values, that is with our activations, so that we can get the theta gradients. So all of this happens inside the loop for each example. Once we have finished all of the examples, we come to the point where we say, okay, now we have the total sum. Let us find the average for theta gradient and average for cost. So we just divide it by n. We add a regularization term, which I said we're not using for now. And once we have the total cost, then we return the cost and the gradient from this function. Okay, so that is the task of this function. Let me execute this and go ahead. So I had stored some values of theta 1 and theta 2. We can just load them up and check with those values if what cost we get. Okay, so nonetheless, we will start with random values and then see how it goes. We also define the predict function. The predict function, once our network is trained, we will use the predict function to find the prediction. Okay. So here again, we just talk with the feed forward path. That is, everything else is similar to the n and cost function. The only difference is we don't need to evaluate cost and we don't need to do backpropagation. We get our output layer. We say, okay, once we have found this percentage, what is the max location? And from that max location, we can evaluate what is our Y prediction. I execute this. Yes, and now we put everything together. So here, putting everything together, we start with our n examples. Put regularization is equal to 0. Keep an alpha of 0.5. Take number of epochs as 22,000. So let me change that to 200 so that it finishes in time for now. We will record our train accuracy and test accuracy for every epoch. So initially, we will create zeros for as many epochs that we have. So this recording of train accuracies and test accuracies will help us to plot our learning curves and thereby see how, in what sense or how good our model is doing. We initialize the number of parameters. We say we put a limit for our random numbers generation. So we keep it from minus e init to plus e init. So here we initialize all our random parameters. We have, once we have that, we convert that into a numpy array to get nn params. And then we run through multiple epochs or multiple iterations. Each iteration, we evaluate the cost and gradient. After we have evaluated the cost and gradient, where are we changing n and here? So we evaluate the cost and gradient. Once we evaluate the cost and gradient, we also, with the present values of n and parameter, we will predict the answer for our train set and test set. Since we have the answers for both of these guys, we'll compare our accuracy, or we evaluate accuracy for train and test, and we will record these accuracies. Once that is done, using the gradient, we will update our parameters. This is the one simple step that updates our gradient descent. That is, new parameters is equal to old parameters minus learning rate times gradient. So once we have updated the parameters, we say, okay, we finished one epoch. we go ahead and do the other epoch and keep doing this successively. Every 10 iterations, we will print the iteration number, we'll print the cost, we'll print the training accuracy and testing accuracy. So that is the strategy. Let me execute this code. And let's see some iterations of what result it is giving. So at the first 10 iterations, we have a cost of 3.3968, a training accuracy of 21%, and a test accuracy of 19.33. And we see as we go every 10 iterations, uh, our training accuracy keeps on increasing. Even our test accuracy keeps on increasing in the same order that our training accuracy is increasing. So we'll have to wait some time for our 200 iterations to complete. I think it should take not much, a few minutes. In the meantime, do you have any questions to ask? Okay. If you observe slowly, we are starting to see a divergence between our train accuracy and our test accuracy. Right, our train accuracy seems to be slightly more optimistic than our test accuracy. Uh, can you guess some reasons for this? No, no idea. Anand?
No, Raja.
So generally, when your train accuracy and your test accuracy start to diverge, it's a point where we are talking
Okay.
about. Hmm, tell me.
Overfitting maybe.
Ah, yes. It's some hint of overfitting. And how can we improve on overfitting? By regularization, right? So we have to change our cost function accordingly, so that we add some incentive for the model to not allow the weights to be high. And if the weights are not high, then we could say that we have achieved some level of regularization. Anyways, in neural networks, there are many more ways in which we can achieve regularization. We'll not go there. So now, let's say we stop. In fact, I could allow it to go higher. And as we go to maybe higher number of iterations, we see that we tend to improve on both train and test accuracy. But since we don't want to wait so long, let's stop at 200 iterations. Let's see our prediction. And let's see, we reach an accuracy of around 84%. These are how our, so we have 100 or around 10,000 parameters. These are first 50 parameters, so that we can see how this will go. Let us not run the regularization. And I had ran this earlier with 2,000 iterations. So luckily we can just go through this list, and we can see that up by the time we reach 2,000 iterations, we have a train accuracy of 94 and a test accuracy of around 89%. And have I run this also? Okay. With more regularization, we go from 89 to 91%. Now, this is MNIST data is fairly simple data, at least in terms of comparing our uh, neural networks. It is good data. Or we can see our models go as high as 95, 96%. And I think the state of the art, that is the best algorithms in the world, gives us around 98% accuracy. So identifying digits is not a problem anymore. I remember when I was doing my bachelor's, we were still comprehending on how we can do optical character recognition, and OCR was not very uh, well known or not very uh, uh, accessible to the market. But now we see that even our OCR has come to a point that many of our mobile phone can scan a few handwritten numbers, and they can convert it automatically. So we have apps that do it. So that means that we have progressed to the point that even your low powered uh, Android phones or mobile phones can have the algorithm for implementing a neural network or to implement some kind of optical character recognition, which is very interesting. Uh, Here are some plots that show our accuracy curves for uh, training and test. We could also try some examples and see how good our model did. So let me go back to our training model with 200 iterations. What is that? Yeah. So here we have our trained model. Let us test it with some numbers and see how good it does. And in fact, I can use the same code as before. Uh, that we were using for plotting. Let me go back up. Okay, this code. We'll see our prediction and we'll see the output together. So we can judge for ourselves how good or bad it is doing. So we'll take 25 random values from 25 random numbers, and from our X train we'll take that data, and instead of getting here Y train, we will print Y prediction. So our Y red new is equal to, we call our prediction function. So our prediction function is this. Copy it, paste it here. Predict with the latest NN parameters. Input layer, hidden layer. Your input will be just this part. And we will write this as a prediction. Okay, hopefully that should hold true. Let us execute this and see what happens. So we get an error. It says all arrays which have the same direction, but array at index 2 is as 1 1. What has gone wrong? We are wrong in this line. So when we're predicting, we are putting X test. Okay. Let me just run this one line separately and see what happens. So here we have an error. What is this? That's our data. I do dot shape. Exactly. Dot shape. Okay. So we have 400 single dimensional data. That is what we expected. If we go back to the predict function and see what it is doing. So if we go back to the predict function, okay, here probably, so end rows and one column, and X shape would be one, X shape should be 400. So here, okay, so we cannot pass just a single example, which is fine. In which case, we can convert, reshape it, and then pass it to the data. So I'll do this dot reshape and -1 and then do its shape. So I have 400 rows and one column. No, I want one row and 400 columns. Since I'm doing just one data at a time, one row 400 columns. So if I pass this, then our predict function should not throw an error. Let me try it out here. Okay, so it predicts the value 5, which is fine. Now we'll verify if that works out. And here I'll replace this again. So copy. Let me execute this. Now we have an error in the next one, which says we byte correct unsupported string. What is this? Let me copy this. So let me put 0 and then looks up. Since this is an array, it says array is not a float number, so we take the 0th element and then execute it. Great. So this is what our model is predicting, and this is what the data is. So let's see if we can see fine. So 0, 0, 3. This barely looks like a 3, but I would also probably guess it is a 3. This here it's a 6, but our model is assuming it's a 5. This it represents that 4, 3, 4, 0, 5, 4, 7, 8, 4, 6, 9, 0, 6, 8, 6, 8. So as I'm going through here, I'm just reading what this is saying, and then 2. Oh, this line it interpreted as 8, which is a mistake. 824. Okay. Very interesting, right? Just some numbers and going through some math and iterating it. Our model has got the ability, at least in this case, we are right. I don't know how many times. We can. Okay, let me also do that. We will. Okay, so this is our prediction, and along with this prediction, we will write y train idx, and our actual answer. Okay, so in the brackets are the actual answers in this. So let us also get our accuracy. Since this works fine, we can say let's start with some ACC is equal to 0, and if these are equal, increment accuracy, and in the end, we will put accuracy is equal to ACC by 25. Okay, so let's check. In this case, we have 80% accuracy, and if I run it again, 92%, and so on. So different scenarios, we have different cases. Sometimes it is easy for our model to predict the answer. Sometimes it is not so easy. So here it seems it has done a mistake. No, 442244. Here 94. So here it has interpreted as a 9, and it's actually a 4. And we can see why it could have interpreted as a 9. It is similar, only the top part is not there, and so the model would have got confused at this point. And so, okay, I hope this is clear, right? Neural networks.
I just have one doubt. Like you said, can you tell me where or when you made the code already?
Anand, your voice is a bit low.
Am I audible now?
Yes, now you're audible.
Okay. So when you how you avoid overfitting actually? How you did the regularization?
Okay, how I avoid overfitting? So,
yes.
So there are multiple ways of doing regularization with neural networks. One is modifying the cost function. So if I go back to my cost function.
The equation you are playing with?
Yes, the equation. Let me go here where we are defining J. So that is inside our NN. Okay, here. So you see, normally this would be J is where we leave it, our cost function. But here we are adding some more ideas to J. Okay, what is the idea? We are saying that in J you add the sum of theta1 squares. That is, you add all of the squares of the parameters for theta1 and theta2. That means if these values are high, then I am adding additional cost. If these values are low, then I have less cost, right? So this sum multiplied by the amount of regularization that I want divided by the total number of terms that we have, okay? Which adds extra incentive to the model to reduce these values of weights. And what we have seen is, if you remember our regularization in linear regression as well, if our weights are less, then we are reducing the order of the equation that represents our hypothesis. Which means by reducing the order, we are also just keeping the most important parameters and reducing the less important parameters. That is what we mean by regularization. Right?
Yeah.
Okay. So this is one way of doing things. In neural networks, we do some other things also. If you go deeper in neural networks, you'll find that we have something called as drop nodes. That means randomly we will pick some hidden layers that we will not train for some of these examples, and we will do it randomly. So we are purposely forcing the model to not train a certain percentage of our hidden layers. And what that would do is, in effect, that would also allow our model to remain simple. And if our model remains simple, then it will it will not be overfit. That's the idea.
It will reduce our accuracy, but if we didn't train few parameters, how it will avoid overfitting? It will reduce our training accuracy.
No, not just training accuracy. It would. So the idea is it will keep those weights small. Okay, and if those weights are small, then we are reducing the order of our equations, right?
Yes.
And if the orders of our equations are small, then instead of, so if you remember the graph that I showed earlier, instead of going this way, you remember for overfitting I showed three graphs. The underfit graph, which was, even though we had a quadratic function, we are representing it using a line. The perfect fit, that is a quadratic function, were representing a parabola. And we had a overfit situation. An overfit situation for a quadratic function, we were using a fifth order equation. The fifth order equation it would have some peaks and valleys where it was not supposed to have it. So if we reduce the weights, those peaks and valleys will be automatically reduced. Even though we have a five order equation, it would act as a parabolic equation.
Okay. Yeah. Yes. Yes.
So here also the same idea holds true. By limiting the weights, by increasing the cost, and we have an incentive of reducing the values of weights. And when we have an incentive to reduce the values of weights, then our hope is that in this complex neural network where we have some 10,000 parameters, those parameters that are not important, or those parameters that may be very high, our model will try to reduce them, thereby improving on overfit.
Yeah.
The concept is same, but here we lose visualization. We cannot understand why it is doing it. But if you take the idea of linear regression, we can probably extrapolate from linear regression what is happening there to what happens in neural networks as well.
Mhm. Yeah.
Do you have any more questions? Srinivas,
Um,
Switcha? Okay. So here, in fact, we end our uh, entire discussion over machine learning, neural networks, anything. Let me just summarize what we have done in our entire course. Uh, we started off with basics of Python, within which we started with learning about operators and control structures. We talked about data types. We talked about functions and modules. We went into another section called as Python packages, where we saw NumPy, pandas, matplotlib, Seaborn, and scikit-learn. We took bits and pieces of scikit-learn when we were doing our machine learning part. We then went into data preprocessing. Here, the key parts were missing values, feature engineering, transformation, integration, and so on. We went to our supervised classification algorithms, within which we saw KNN. Let me put all algorithms at one go. KNN, decision trees, random forest, naive Bayes. We saw different strategies of validation. So three-way split, cross-validation, and stratified cross-validation. We did a lot of data sets here. So we started off with Titanic. Mhm. For explaining earlier, we also did Iris, but let's skip that. We did heart disease prediction. We did human activity. Okay. We did then supervised regression. in which we just saw one algorithm, linear regression, and then we saw two other algorithms which are very similar to linear regression, only that they have a different regularization term. Here, I think we also talked somewhere in between, we also talked about fitting, and we talked about fine tuning using grid search and randomized grid search CV and randomized search CV. Here we tried our implementation and testing with house price prediction. We came to unsupervised, and here we talked about clustering algorithms. We saw k-means and hierarchical clustering. And we tried only one data set, that was a student survey data set. And finally, we went to neural networks, in which we saw our one blue, three brown videos, which were basically talking about layers, talking about gradient descent. And we implemented neural networks with MNIST dataset. Okay, so it's been a long journey. Uh, we in fact had 40 hours. 40 hours is uh, how long it takes to have one subject in an engineering course. Of course, we have not covered everything. Data science is way huge. Okay, and even now, I am continuously learning on so many methods and improvements that do happen. So, as I said earlier, if you remember probably our initial classes, there are some excellent resources online that can help you to continue studying. One big resource is Kaggle. So participating in Kaggle competitions or participating in one data set a week at least keeps you up to date or keeps you on the edge of learning more and seeing how other programmers are coding. Looking at their notebooks can also teach us uh, teach us on what are tips and methods what other people are using, and over a period of time you can get your own style and you can uh, adapt or become better, create more libraries and so on. Kaggle is an excellent resource. I read multiple blogs on data science, so towards data science is a huge uh, place to learn. Another place is analytics vidya. Few podcasts to follow is OC Devil 101 or Data Skeptic. So these are podcasts. These are blogs. That's it. Of course, you can also additionally take Coursera courses. So I would highly suggest, if you want to take a course, start a course by Andrew Ng. He will go from the basics of math to implementation to really advanced concepts. So Andrew Ng has multiple free courses on Coursera, starting with introduction to machine learning, introduction to neural networks, introduction to deep neural networks, and so on. Yeah, these are excellent resources that can help you. I think there are few very good books also available. Uh, One book that I used to refer is Hands-on ML with Scikit-learn and Keras, and TensorFlow. So TensorFlow is a neural network library by Google. Uh, it's quite complex to wrap our heads around, at least in the beginning. So people use another library called as Keras, which is a high-level library that helps us do neural networks, define network structures, and so on. But then again, I would say those are advanced concepts in terms of not advanced in terms of understanding, but advanced in terms of usage and the kind of problems that we're trying to solve. But I think with this background that we have done so far, you could go ahead and explore these resources, materials, and ideas so that you can improve further. Uh, uh, any career choice that you make never ends at a fixed point. You continuously keep on learning. So here also, if you are planning or aiming to become a data scientist, it comes with a lifelong learning curve, and we need to continuously keep updating ourselves so that we do better and better. Okay. Do you have any questions or comments so far? Okay. Okay, great then. I think we are done. Those YouTube videos will stay there, but probably I would suggest from our Google Classroom, if you need to download some material, you can download and keep with you. Uh, I'll not remove them now, but sometime, someday, my Google Drive will get populated. There will be no more space there. So maybe in the future, you cannot trust it will stay there always. So I would suggest all our material, maybe slides, notebooks, and so on, you can download from the Google Classroom and keep it in your own repository. That can help you in if you later on you want to revise something. The video will stay there. You can check the video and go through this material, or you can contact me also. So either way works fine. Okay.
Yes, thank you, Raja.
Yeah, thank you so much. It was a good learning experience. Uh,
We will meet later.
yeah, we'll meet later.
Goodbye, no need of that.
What?
No need of official goodbye speech. So there's no point in that.
Yeah, sure.
Okay, then. Bye.
Okay, bye.
Thank you, Elijah. I'll
Thank
reach
you.
out if I have any question. Thank
Yes,
you so
yes,
much.
surely. Thank you. Bye bye.
Yeah, thank you. Bye.
Thank you. Bye.
Bye, Switcha. Bye.